This course is on heterogeneous catalysis and catalytic process. The catalytic process, which is one of the most important reactor application for transformation of reactants into products. The basic of this course will involve that different type of catalysts used in process industries, whether it is a pharmaceutical industry or a hydrocarbon, petroleum, refinery industry, and their selection, some design, then some reactor design applications, and then finally some catalytic process which are commercially used in industry, and then some environmental aspects of this. So, today's lecture will mainly talk on introduction and basic concepts of green catalysis, because now every transformation process of reactant into product is related to the environment, sustainable development of environment, that is ecological and whatever the environmental concerns today that deals, and that concept is known as green chemistry. What is catalysis? That is the first question in mind, that how a catalyst works and the basic principles. So, the definition, there are numerous definitions. If you look at the literature, lot of definitions are available on catalysis, but the basic definition, if you look at a catalysis, is an action by catalysts which takes part in a chemical reaction process and can alter the rate of reaction, and yet itself returns to its original form without being consumed or destroyed at the end of the reaction. So, this is one definition of catalysis. So, catalysis is basically the application of catalyst for transformation of reactants into the products. So, catalysis is a process and catalyst is a substance which reacts during the process, but at the end it emerges as an unreacted raw material. So, but does not mean that catalyst does not take part in reaction, it does take, and definitely due to the course of time there are several reactions and secondary reactions which take place on the surface of the catalyst, and because of that its activity or life or the property also deteriorates. But the definition wise, if you look at it, is a substance which does not take part in the reaction. So, basically the purpose of using a catalyst in a process is to speed up the reaction, because the thermodynamics is one where you look at the equilibrium kinetics and the rate of reaction can be increased in the presence of catalyst, but the final or equilibrium conversion, what you call the maximum conversion, that cannot be changed. So, basically when you have a catalyst in the process, you are trying to enhance the rate of reaction. In one way, what we say, it is the energy or activation energy which is required to activate the process or to make a the complex during the reaction, that is reduced. We will talk on that. So, presently if you look at, it is a key to chemical transformation in all industrially benign process. So, whether you look at any fertilizer industry, refinery, petrochemical, pharmaceutical, the catalysts are being used, right, and more than 95% or I will say 90 to 95% process are generally being run in the presence of catalysts. The important aspects in catalytic process, if you look at the, as I said before also, that it will change itself during the process by interacting with other reactant product molecules. So, this thing I will discuss in detail later, but basically it is something on a surface of a catalyst, the reactant molecule come to the surface of the solid, and then it transform into the secondary reaction, what you call mechanism of the reaction. So, that we will discuss in detail later, but basically when we see here that a catalyst is adsorbed on the surface, the reactant is adsorbed on the surface of the solid and then transform it to some intermediate, and that intermediate transforms into the product. So, there is, if you look at net change in the Gibbs free energy, that is from thermodynamics, that does not change, because it is nothing but based on reactant and the product side. So, this is the first thing here, that it will change itself during the process by interacting with other reactant or product or molecule, and it can alter the rate of reaction, right. So, that is another important aspect. Suppose if I just say that a reaction where you have the carbon monoxide, if you just look at this CO plus hydrogen on a metal substance, it can give you a paraffin. Suppose if I have a metal something like So, this is a paraffin hydrocarbon which is a straight chain hydrocarbon which will have molecular formula of CnH2n plus 2, something like this. So, CnH2n plus 2, and if the metal is something like your cobalt. So, a metal cobalt can transform these two reactants, carbon monoxide and hydrogen, to a paraffin which is your diesel range of hydrocarbon. If you have something on iron as a catalyst or metal, then this can give you olefins CnH2n, and which can be isomerized or hydroisomerized, and you can get from this the gasoline or petrol range of hydrocarbon. If you have something like a different metal which is copper oxide, then it can give you sometime in zinc oxide also, then you can get alcohols from this like methanol. So, you can see very clearly here that by same reactant carbon monoxide and hydrogen, but with different metals, the product distribution or products are different, and this is the key here, the selection of a metal for a given reaction. So, it means the same reactant can be transformed to different type of products depending upon the catalyst. So, this is the key here in the reactor application or process application for a catalytic reaction. So, one can control these reactions in order to get a desired product. So, this means that in most of the cases, if you look at, the rate of reactions are increased by the catalyst. However, in some situations the rate of undesired reactions or selectivity suppressed. So, this is what I was talking in this reaction, that when you have a carbon monoxide and hydrogen, it can give you alcohol, it can give you olefins, paraffins, naphthenes, and a series of hydrocarbon. But what is your requirement? Basically, according to that, you have to select a definite combination of metal and support, and of course the optimization of the process condition. So, this becomes a key in the selection of a metal, selection of a support, and then application of these metal support for a given reaction. So, again we have seen that catalyst comes to its original form, which is a general definition, but due to the several secondary reactions on the metal surface, the activity of the catalyst may change during the course of time. So, that is what you call the deactivation or decrease in activity of the catalyst, which we will see later. After reaction cycles, a catalyst with exactly same nature is reborn. This is what the definition of catalyst we said, that it does not take part in the reaction, right. In practice, the catalyst has its lifespan and deactivates gradually during use. This is what I was talking here. So, in general, if you look at, the definition is that the catalyst accelerates a chemical reaction without affecting the position of the equilibrium, right. But if you look at, apart from accelerating reaction, catalyst can affect the selectivity of various chemical reactions, right. So, that is what the, just like the syngas application I told, the different product distribution or the different distribution of products can be obtained from a given starting material by using different catalytic system. So, now what is catalyst? We have seen that it alters the rate of reaction with high selectivity. So, selectivity, the definition of selectivity is basically is nothing but the moles of some desired product divided by moles of undesired product. There can be different definitions of selectivity also. This can be defined the moles of desired product per mole of the reactant which is reacted, right, because the suppose syngas is reacting and you are getting paraffin, and suppose paraffin is the desired product. So, moles of paraffin produced or diesel produced per mole of syngas reacted, or it can be moles of diesel produced divided by moles of all the other hydrocarbons which are produced. So, there can be different definitions of selectivity, and depending upon the requirement or optimization of process conditions, we look at that definition and we use it in the process, right, during the design. So, basically the catalyst alters the rate of reaction. So, there are several other questions when you look at this point, then does it participate in the reaction. So, as I said that yes, catalyst participate in the reaction because it makes the intermediate, and the route of when you have a non-catalytic reaction, then the mechanism may be different, and when you have a catalyst, then the mechanism may be different, right. How does it change the rate? Another question. So, we said that it offers an alternate path with low activation energy. So, E refers here the activation energy, I will talk on that. So, basically activation energy is minimum amount of energy required, right, to activate a reaction. So, because when you see a reaction, the reactant products reach to a level of intermediate state, right, which is called a transition state. So, when you have a non-catalytic reaction, the reaction can happen, right, just like if you look at that environment has lot of nitrogen and oxygen, right. So, and luckily it does not react, right, because the temperature conditions and catalyst is not there, right. So, there may be some NO formation because of that, but it is not in excess, otherwise we will have oxygen deficiency. But if you look at the Ostwald process where you look the nitrogen and oxygen reaction to form the nitric oxide for HNO3 manufacture, you need a catalyst, right, and there we want a more conversion of nitrogen in presence of oxygen to form more and more nitric oxide and then react it with water and give you nitric acid. So, that is again key of the post-Wald process for HNO3 formation, right. So, you use some catalyst there. So, I mean to say here is that the catalyst for a reaction is required to reduce this activation energy, because when the activation energy is reduced, then at a lower temperature the reaction can be processed, that is one thing, or if you have same temperature the rate towards that process can be increased. So, this is the key in a catalytic process, that it reduces the activation energy for a given reaction. So, again, does it affect the heat of reaction? Delta HR refers to heat of reaction, delta GR refers to the Gibbs free energy, right, and equilibrium constant. So, these things are generally defined from thermodynamics. So, as I said before, catalyst can never change the equilibrium, right. The catalyst can change the rate or approach towards reaching the equilibrium. So, your reaction can be faster, but your maximum conversion, which is governed from the thermodynamics, that cannot be changed in presence of catalyst, right. So, basically you know that when a chemical reaction happens, it reduces the free energy should be decreased, right, it decreases the free energy, and as soon as the reaction processes, the negativity of Gibbs free energy reduces. So, finally it will come to 0. So, when the Gibbs free energy is 0, delta G is 0, no chemical reaction. So, that is what you call system is at equilibrium. So, when you have a catalyst in the process, the rate towards that is increased, that is one thing, and delta G, which we are calling Gibbs free energy, is related to your delta H minus T delta S. So, actually this is thermodynamics. When you look at a delta G for a given chemical reaction, this is known as Gibbs free energy, or basically this is the useful energy, is equal to delta H minus T delta S, where this term is entropy, delta S is known as entropy. So, this is basically the total energy is this delta HR heat of reaction, and this is the amount which has been transferred to the surrounding. So, net total energy is this minus this, and that is your useful energy. Right? And for a chemical reaction to happen, delta G should be negative. So, less than 0, then only the chemical reaction will take place. And when delta G approaches to 0, then it means speed of the process is decreasing. So, how much you are away from the equilibrium, it means you are increasing the rate, right. So, that is what the key in the reactor design. So, we use now a different concept for reactor design also, like say membrane reactor or separate the product. So, membrane distillation process. So, every process where you are removing the products during the course of reaction, so you are disturbing the equilibrium, right, in a process. So, that is what the rate towards that will increase when you have the deviation from the equilibrium. So, catalyst cannot affect these 3 points, but the equilibrium constant cannot be changed. So, equilibrium constant is a function of temperature, right. So, endothermic, exothermic, different kind of chemical reaction. So, according to that your value will change, but otherwise the catalyst cannot change the equilibrium constant of a given reaction. So, again, does it affect yield and selectivity? So, catalyst can affect, yes, as I said that different type of metals can be selected. So, the rate towards a given process can be increased, right. So, yield and selectivity can be affected in the presence of catalyst. Does it initiate a reaction? So, catalyst can initiate a reaction. So, sometimes the reaction cannot happen even at but when you have a catalyst in the system, initiate the reaction, right. So, that is the key of a catalyst. So, sometimes the reaction may not happen in the absence of catalyst, but when you have a metal on that reactive species can adsorb and then it can transform into a product. So, if you look at what the catalyst does, so that is what we are talking here. If you look at this, so A and B, these two reactants, and they are adsorb on a surface of a catalyst. So, this is a catalyst. So, something is happening on the surface. So, it is a kind of bonding of A or B, or this can be on the gas, this can be on the gas, or both can be on the surface of the solid. Then they in this case here A and B both are adsorbed and they are transforming into some complex AB star, something like that, and that complex again on the surface of the catalyst it can diffuse or it can transform into a product like P. So, this is a adsorb P on a surface of a catalyst, right. So, details of these mechanism we will discuss. So, these are the keys of the reactor design also, because how big is your reactor or how small is your reactor will depend on these selections of this metal, this, and then suppression of this, right. Because the basic idea is that if you have reaction is highly activated, right, or rate of reaction is very fast, so size of the reactor can be reduced. So, due concept of this nowadays atom efficiency or whatever E factor we call, that are the key in terms of the catalyst design and green catalysis concepts also. So, you have a P and you may have a unreacted reactant and the product. So, you get it separated or catalyst separation from the product, and then finally, you have a product here. So, this is what the overall action of a catalyst. So, if you look at here, in every catalytic reaction, this is a sequence of elementary steps. So, because I expect that all of you have some knowledge of the chemical reaction engineering. So, you know what is the elementary type of reaction and non-elementary. So, basically the elementary reaction we say that directly the reaction is in terms of the stoichiometric coefficient. When you talk a non-elementary, the rate may not depend on the stoichiometry of the reactants, right. A goes to B, what is here, it is overall reaction is A plus B gives you P, right, but this is not the case here, because A plus B gives you something like AB, and then AB transforms into P star, or AB star transforms to P star, and then P star goes to the product. So, basically, so this is the meaning that every catalytic reaction is a sequence of elementary steps. So, every step is now elementary, but overall step are non-elementary. If you look at overall reaction, that is non-elementary type, right. So, in which a reactant molecule bind to the catalyst where they react, after which the product detached from the catalyst and liberating the later from the next cycle. So, this cycle continues. So, catalysts are free always, or catalyst is free from the reaction. And the same picture where I was talking about the catalyst lowers the activation energy, right. So, sometimes the reaction can happen in the absence of catalyst. So, this is the Gibbs free energy, what is the delta G for a reaction, and this is the extent of reaction, or sometimes you call reaction coordinate also, right. So, if you look at here, that this is the actual path when there is no catalyst in the system, right, and when you have a catalyst in the system, there are adsorption, right, some surface reaction, some desorption. So, reaction is exothermic. If it is adsorption, basically the something absorbing on the surface of the solid. So, reaction is exothermic. That adsorption is generally considered exothermic reaction, and when you have desorption, it is the endothermic reaction. So, these are the peaks which are talking in terms of adsorption and desorption. So, basically the transition state or some kind of star which has formed here, right. So, the catalyst has lowered this activation energy for this reaction basically, which is something like A plus B, which we are talking here, a formation of this. So, this can happen only in the presence of catalyst. When you have no catalyst in the system, then it may happen that you may need a large temperature, right, or some severe reaction conditions. So, the uncatalyzed reactions that has higher Gibbs free energy of activation delta G, and then any step in the synthesized catalyst reaction. This is the first thing, right. The Gibbs free energy reaction delta G for the overall reaction is unchanged from A to B, because your product is here, right, reactant is here. So, your net change which you call enthalpy of product minus enthalpy of reactant, that is same. This is just like a point property, right. So, the total Gibbs free energy for the reaction will not change, but for activation energy or free energy which is here compared to catalytic reaction. So, this barrier is now reduced. So, the reaction can happen at lower temperature, or if you have same temperature, the rate of reaction will be higher. So, if you look at action of a catalyst now, how does catalyst act? So, reaction activation energy is altered, that is what the lowered basically. So, when you have a catalyst in the system, the activation energy for the reaction is reduced, right. The intermediates formed are different from those formed in the non-catalytic reaction, because when you have no catalyst in the system, the reaction is a kind of free radical reaction. So, that will be in the gas space. But when you have a catalyst in the system, the reaction is on the adsorbed surface. So, it is a kind of adsorption and surface reaction, which we will see later in the mechanism. But basically the mechanism is changed when you have a catalyst in the system. So, this is what the intermediates will form, will be of different type. So, that is what the example which we have given for syngas or GTL nowadays called. So, syngas conversion to liquid fuel, when you see, you can get a series of the product, right. A simple component, if I just say from methane conversion, and methane can go to your wax also, C60, C80 range of hydrocarbon, very high range, right. And if you have a selected catalyst, you can just get a narrowed down product distribution, something like C5 to C10, which is your gasoline, or C12 to C20, a diesel range, right. So, paraffins can be there, straight chain hydrocarbons, right, naphthenes can be there, cycloparaffins, aromatics can be there, alcohols can be there. So, series of the product can be obtained when you have a catalyst in the system, and that is what we are talking as selectivity, because you can get series of the product, but how to narrow down this product to have a valuable product for the reaction, or high selectivity for a valuable product, that is the key in the catalysis selection. The reaction, when you have a catalyst in the system, the reaction can happen under less demanding conditions like temperature, pressure. So, part of the things are governed from your thermodynamics, but the rate towards that can be governed in the presence of a catalyst, or different type of catalyst will have different kind of rate, but equilibrium will remain same. Just note down that point. And the catalyst allow reaction to occur under milder condition, e.g. at lower temperature for those of heat sensitive material. So, if you have something where the component which can decompose at higher temperature, there the reactions need a certain kind of specific action. So, there the catalyst can play a role, right. Most of the time when you look at the enzyme type reaction, where they are very much sensitive to pH, very much sensitive to concentration of acid or temperature, then a suitable catalyst can help to happen the reaction under those ideal conditions. So, the selection of a catalyst will be the crucial there, and this can happen in the presence of catalyst. And it is important to remember that the use of catalyst does not change delta G and equilibrium constant, that I have said, and that is the catalyst can only speed up the reaction, but cannot change the reaction, right. So, basically the thermodynamics plays a very crucial role, that whether a chemical reaction, when you are looking A plus B converting into C plus D, the first important thing is that read the thermodynamics, understand the thermodynamics, calculate the Gibbs free energy for that, and delta G has to be negative, then only the reaction is possible. So, you have to look at the delta G, which is from your whatever your equation from delta G minus RT ln of K is equilibrium constant, calculate the equilibrium constant, which is function of temperature depending upon the endothermic or exothermic reaction, and then calculate delta G at different temperatures, right. So, when you have to select the temperature, minimum temperature required for a reaction, so wherever your Gibbs free energy starts negative, then your reaction will proceed at that temperature. So, that is the first thing. So, the catalyst cannot do anything in that regard, right. So, reaction thermodynamics provides a driving force for a reaction. The presence of catalyst changes the way how driving force acts on that process. So, I am just speaking these words repeatedly because the thermodynamics is the first part for a chemical reaction to happen, right. You have to just look at that whether a reaction is really possible from thermodynamics or not. Just as an example, I have shown you here the dry reforming. Basically, this reaction has lot of importance nowadays, because this two greenhouse gas, methane and carbon dioxide, they are available and cause the greenhouse effect. So, methane and carbon dioxide can be converted to carbon monoxide and hydrogen. So, this is a very important process because this gives you the oxy-alcohols, this gives the syngas in the ratio of 1:1, and that can have the application in the production of either dimethyl ether or alcohols, right, or this can be used as a power generation system also. So, if you look at the just at 373 degree Kelvin, this is the temperature at Kelvin, the Gibbs free energy is 151 kilojoule per mole, right. So, 100 degree centigrade means the reaction is not possible, right. If you look at Gibbs free energy at 973 Kelvin, minus 16 kilojoule, right. So, it means at 700 degree centigrade this reaction is possible because the delta G is negative. So, when delta G is negative, the reaction is possible. So, if you just enhance the temperature, this will still go towards the negative side, right. So, and then it will come as the reaction proceeds, this delta G value will decrease and finally it will come to a 0 level. So, it means the reaction is at equilibrium now. So, that time the does not mean the equilibrium does not mean that reaction is stopped. There is a reaction, but the rate of forward reaction is equal to rate of backward reaction. So, the reactants are converting into products, products are converting into reactant at the same rate. So, effectively there is no additional conversion, right. So, at 100 degree centigrade the delta G value which is greater than 0. So, there is no thermodynamic driving force, the reaction won't proceed with or without a catalyst. So, this is very important here to understand. Same thing here at 700 degree or 973 Kelvin, this is 973. So, 973 Kelvin delta G is minus 16 kilojoule per mole. So, thermodynamic driving force is there. However, simply putting methane and carbon dioxide together in a reactor does not mean they will react. This is very important. Without a proper catalyst heating, the mixture in the reactor results no conversion of methane and carbon dioxide, right. So, a catalyst is required. So, in this case a platinum zirconia or nickel alumina, these catalysts can happen the reaction at a faster rate, right. So, these are the key for the reaction of dry reforming of methane, right, that is known as dry reforming of methane or methane carbon dioxide reforming. So, action of catalyst, what we have read so far is that catalytic action, reaction kinetics and mechanism very important, right. So, what is the kinetics of a reaction, that you call overall kinetics, but how that overall kinetics appear in terms of rate determining step for a reactor design, that becomes important. So, we need to understand how methane is adsorbing on the surface, how carbon dioxide is adsorbing on the surface by catalyst, and then how these two adsorb species reacts and transform into a syngas, right, and then how the product dissolves. So, that will be the key in terms of enhancing the rate towards equilibrium or increasing the rate, and that will help in reactor design. So, catalytic action leads to a rate of reaction to change, right. This is realized by changing the course of reaction compared to the non-catalytic reaction. So, a complex forms, right. So, forming complex with reactants or products, controlling the rate of elementary steps in the process. So, a particular step of a reaction controls the rate, not all the steps will be rate controlling. So, generally it is something like a rate driving or whatever the slowest step of that rate will be the controlling step. So, we have to find out the kinetics for each, rate of reaction for each term, their activation energy and then rate constant. The lowest or slowest step of that reaction will be called as the rate governing step. So, it means these are kind of resistances which are offered during the course of reaction, and we have to look at, when we design the reaction, we just focus on our slowest step because that is controlling the total efficiency of the process, right. The concept of green catalysis nowadays is very common. So, everybody is talking in terms of green technology, green chemistry and green environment, sustainable environment. The meaning of this is that whatever the technology which is being developed or whatever the old technology, that should be revamped in such a way that the waste production should be minimum, right, and the environment should not be affected. So, there in all, if you look at, the catalyst plays a very important role, and that is why the catalyst is nowadays a $1 billion business, right. The new catalyst, novel catalyst, in terms of selectivity, in terms of their efficiency for the process and in terms of the waste minimization, a novelty is to be developed or lot of R&D scope is available in terms of catalyst development or new process development using the catalyst or using the concept of green catalysis, right. So, basically the meaning of green catalysis is that the technology which you are developing, that should be of low cost, right, cost should be low and can be easily scalable, right, because sometimes when you look at the large scale plants, the technology may not be successful, right. In a small scale or lab scale, the data may be generated, the results may be excellent, but when you try to scale up the process, it fails. So, that is the meaning is that the technology or catalyst which is developed, that should be scalable. Renewable starting material. So, new concept is again that the source, because just like as an example, crude oil sources are limited, right. The life of crude oil is expected to be just 60 years. So, now the new concept is that use some kind of renewable fuels or renewable energy like biomass, algae biomass, solar, wind. So, these kind of new nuclear. So, these kind of energy sources may be useful to fulfill the demand of the future. So, new starting materials should be used. Environment friendly operation. So, the technology which is to be developed or being developed, that should not affect the environment. So, the carbon dioxide, say, that is what the carbon taxing or the carbon dioxide causing the greenhouse global warming potential. So, the amount of carbon dioxide to the environment should be reduced. Similarly, the toxic gases which are produced during the process should be at its minimum level. So, Environmental Protection Act or the Euro norms, these should be satisfied when the new technology or new catalyst is being developed or is to be used in a process. So, this is an eco-friendly approach for a given process. Specialty chemicals, the catalysts are widely used for the fine chemicals, specialty chemicals, right. So, there the waste production is very high, because when you look at the specialty chemicals, especially the pharmaceutical industry, the purity desired is 99.99%. So, in that case, when you have a good catalyst, if you design a good catalyst to select, then you can minimize the waste, right, because otherwise the production, the efficiency what I am talking is that now the waste should be minimum. So, that can happen only when your process is optimized, well optimized, or the catalyst which is developed or which is used for the process is highly effective, right. So, that is again the for specialty chemicals and pharmaceutical industry, the application of this is very important, and green catalysis concept is being used nowadays. Non-toxic byproducts. So, byproducts should be reused in the process, or byproducts should be used for some other process. So, that is again the process concept of the green catalysis. If you just look at the comparative measurements, right, when we look at the selection of a catalyst, that is the first thing, which is the best catalyst. So, catalyst screening, right. Then determination of the process parameters, like when you optimize the process, you need to learn the kinetics, and then you have to find out the optimum process variables for the catalyst process or catalyst production condition, and then simultaneously stability of the catalyst, because for how much time the catalyst can be used, because if you look at the refineries, petrochemical industry, the feedstocks are heavier nowadays, right. Atmospheric residue, vacuum residue, they are being used for cracking operation, right, or for production of gasoline, FCC process, fluid catalytic cracking process. So, the deactivation of catalyst may be very significant, right. So, the novelty is that the catalyst should be successful and should be used for a longer period, or should be reused for some other process if it deactivates after certain period of time. So, these are the new challenges in terms of the green catalytic process. So, when you look at the catalytic selection or screening, so conversion under constant condition, that is the first thing, you compare all the catalysts, right, A, B, C, 3 different catalysts suppose you have. So, first thing is that understand from the chemistry side, which for a given reaction which catalyst will be good, right. So, some metals may be good, right, metal oxides may be good. So, and once you have selected these metals, so molecules will come onto the surface and their orientation. So, design of that, right, the support, metal support structure which you are designing, the preparation methods are very important, very crucial, because the molecules comes onto the surface and adsorb. So, how does a molecule adsorb? It is very strongly adsorb, it does not work. If it is very weak adsorb, then also it will not work. So, a suitable kind of tuning is desired between the reactant molecule and the metal support. So, that is the crucial point in the reaction, catalytic reaction. So, we compare the different catalysts, that is in the terms of conversion. So, you make the identical condition based on either design of experiments, right, or some optimization tool like response surface methodology. You select that these kind of methods where the catalyst can be tested in terms of temperature, in terms of pressure, partial pressure, so concentration. So, all you identify the parameter and test the catalyst, all catalysts under the same condition, and then look at the conversion, right. Same thing for a given space velocity, as I said, and make the conversion constant, and then again compare the performance, right. For a given space velocity, your conversion will decrease, right. So, you try to maintain that a balance between them and then compare. Space time yield, again, that is with space time how the product yield change. So, that is again a crucial factor, because the you are looking in terms of the product distribution. So, selectivity may change, right. Temperature required for a given conversion. So, all these parameters need to be selected for the selection of a batch catalyst or design of a catalyst. So, basically catalysts are generally investigated based on a given reactor. It may be a fixed bed reactor, it may be fluidized bed, batch, CSTR. So, depending upon the reaction, we select a reactor and then test the conversion at constant space time, and then compare the performance in terms of conversion, right. So, basically the space time, space velocity, I hope you know all these terms. So, basically space time is nothing but a kind of W by Fa naught. I can just define it here. Space time So, basically we define for a catalytic reaction in terms of the mass of catalyst divided by the feed rate of a limiting component, right. So, W is the mass of catalyst, this can be in gram, this can be in kilogram, right. Feed rate can be in different units. So, generally it can be gram per hour, something like this, right, or gram mole per hour. So, that is the feed of a limiting component. So, basically it has the unit of time, right. So, idea is that when you have a fixed bed reactor, so this is your mass of the catalyst W, and the feed is coming from here Fa naught. So, how much time the reactant species is spent in a catalytic bed, in this bed, right, and depending upon that you will have a conversion. So, for a fixed condition you are calculating or comparing the conversion, and space velocity is opposite of this. So, this is basically Fa naught by W. So, it will have a unit of time inverse, right. So, basically it is giving that how many reactor volumes can be treated in a given time, unit time rather, right. So, both are or both terms can be used interchangeably when you look at the catalyst performance or reactor design. This is just an example for comparing a catalyst. So, space time yield I have already defined desired product quantity per unit mass of the catalyst or per unit volume of catalyst per unit time. So, that is another term of space time yield. So, when you look at a chemical reaction, you are comparing the conversion as a function of space velocity, which is either in terms of feed rate divided by mass of catalyst in terms of volumetric feed rate or molar feed rate or gram feed rate. So, a catalyst A which has conversion like this X1 here, this catalyst B which has conversion X2 at the identical condition, right. So, basically in this case if you look at X1 greater than X2, so you can say that this catalyst is better, but this is not a correct understanding, because the conversion high does not mean that the catalyst is good. So, simultaneously you have to look at this thing also, yield of that desired product, right. So, because suppose if I have an aromatic hydrocarbon or if I take the atmospheric gas oil, crack it, everything can go to the carbon, because if you have very high space time, very high temperature, these molecules will react and give you some kind of polycondensed aromatic hydrocarbon, right, coke. So, you need a gasoline, right. So, in that case your desired product, what you call space time yield or moles of the gasoline produced per unit mass of the catalyst per unit time is very low, right. That is space time yield. So, in that case the conversion is high, but desired product yield is low. So, the catalyst is not good, right. So, sometimes the high conversion does not mean the catalyst is good. The catalyst will be good if at the same conversion level the product quality or desired product amount is also high. So, that is why we talk in terms of space time yield. So, something like that, the carbon formation should be minimized when you look at atmospheric gas oil cracking, and gasoline yield should be high, right. So, you have to optimize or you have to tune when you select a catalyst for a given reaction. So, now when I said that conversion may not be very important, the selection of a catalyst becomes a challenge, right. On what basis you select a catalyst for a given process, right. As I said that you optimize the process condition, you look at the do the design of experiment, but for what, right. You have to look at that, you have to compare from the results from thermodynamics, right, and look at the desired product yields, desired product selectivity, right. So, this is what the suitability of catalyst when you look at for any industrial process, this will depend on activity of a catalyst. So, activity is something like conversion, right. How fast is the conversion in the presence of a catalyst, right. So, catalyst is transforming into a reactant species into product. So, how fast that catalyst can work. So, because faster this activity of a catalyst, smaller will be size of reactor, what you have seen in your WY-FNO effect, right. So, this is what this size of a reactor can be reduced if you have very active catalyst. So, the commercial reactors, if you look at industrial reactor, they are very large in size. So, now the new trend when you look at, you design a catalyst in such a way it should be highly activated, right. So, if the catalyst is more active, the size of the reactor can be reduced, and these are what your compact type of reactors, right, just like a heat exchanger, on-board reactors. So, they can be useful, right, space consumption is less, and the same design the critical conditions of design that will be reduced when your size is lower. So, all these things they are very viable when you look at a novel catalyst, and the technology in terms of the total economy of the process that can be reduced, right. So, activity is very important, first thing, then selectivity, which I told, space time yield or desired product. Stability is related to the deactivation behavior, because sometimes the catalyst may be very active in the initial period, right. Just for say your design developed a catalyst for 10 hours, the activity may be very high, right, but after 10 hours the activity drops faster and becomes 0 after say 15 hours, right. Catalyst B, the initial activity is low, but it can last for say 100 hours. So, you have to find out which catalyst is good, right. So, in that case, the stability that we need a catalyst which should be stable also. So, a good catalyst, when you look at from green catalysis process, because when your catalyst is deactivated, you have to dispose it, right, and disposal of this type of solid waste is also a challenge, right. We need to find out that what are the process which can be used for the disposal or safe disposal or reuse of these catalysts. So, if you have a catalyst which has longer life for a given conversion or given activity or selectivity of a product, then it is good, right. So, we need to select a catalyst, or we need to design a catalyst as per these terms and conditions. So, the question which of these functions is most important is generally difficult to answer, as I said, right, because demands made on the catalyst are different for each process. So, sometimes we talk in terms of selectivity, very high selectivity, sometimes we talk in terms of stability, or you tune it in terms of the process selectivity and stability, design a novel reactor, right. You can do a fluidized bed reactor, right. You can have a moving bed reactor where the catalyst deactivation is faster, but conversion is high, selectivity is high. So, you transfer in a given time into a second reactor, regenerate it and take it back, right, just like in a fluid catalytic cracking FCC reactor, they are based on that, right. So, reactor regenerator combination that can also be taken or considered, but this depends on the demands or for a given catalytic process in terms of economy or reactor design concept. Definition wise we have already discussed. So, activity generally is measure of how fast one or more reaction proceeds in the presence of catalyst. So, how fast the reaction transforms, reactant transform into a product, that is related to the activity of a catalyst. So, basically conversion also you can say that, right. So, activity can be defined in terms of kinetic forms, right, that is basically in terms of more practicable or oriented viewpoint, that is the rate of reaction, generally what you call the moles of a reactant transform into the product per unit time per gram of catalyst, right, or just moles of product formed per gram of catalyst per unit time, or moles of reactant reacted per gram catalyst per unit time. So, any definition can be used to define this activity of a catalyst, right. So, just most of the time we talk the reactant reacted per unit time per gram catalyst. So, related to the rate. So, how this rate change with time or temperature, that can also be defined in terms of activity. So, in general conversion, what I defined, moles reacted divide by whatever the fed, right, into 100. So, that is known as percentage conversion. So, percentage conversion can also be defined in terms of the activity. The different catalysts when you select for a process, right, they may have different activity, they may have different selectivity. But when you select the catalyst, suppose I am taking different mass. So, suppose I am taking catalyst A, catalyst B, right. This is say 10% nickel on alumina. So, generally we define catalyst like this, a combination of metal and a support. So, this is 10% nickel on alumina, it means total weight is 100 gram and out of that 10 gram is the nickel. So, alumina may be 90, right. Same thing, suppose if I have taken another catalyst which is 20% nickel on alumina. So, you are comparing these two catalysts. So, obviously, suppose if I get with this catalyst 50% conversion and with this catalyst say 45% conversion, right. So, you have two values of conversion x1 and x2. So, how to select which catalyst is good? So, we define a term which is known as turnover frequency. So, basically what is turnover frequency? That is not related to the mass of the catalyst. You have taken same mass of the catalyst here 1 gram, here also say 1 gram. So, we are comparing now based on some active centers, because what I said, on a metal support, this is your alumina support, and on that you have nickel metal. So, does not mean that higher amount of nickel, when you load it, it gives you higher selectivity, higher conversion. What is important is that these active centers, how they are deposited on the surface or distributed on this support, right. So, that is known as metal dispersion. So, the good definition, instead of defining the rate, because conversion when I am saying, it is basically related to rate, right, the moles of a reacted per gram of catalyst per unit time. Here what I can do, we can define the definition in terms of per gram of nickel reacted or per gram of nickel which is active for the reaction, how many molecules of that reactant species converted, like something like if I am talking the ethanol reforming. So, how many molecules of ethanol are reacted per gram of nickel. So, this 1 gram of this catalyst if I am taking, right, in total mass. So, the total concentration which you see here is just 0.1, right, total mass of the catalyst. So, this is 0.1, here it is 0.2, right, and out of that how many are active, does not mean that suppose in 1 gram catalyst this is 0.2 gram of this or 0.1 gram here, 0.2 gram here, does not mean that all 0.2 gram, if you calculate in terms of number of gram molecules which are available on surface, right, that may not be same, because the molecules may have deposited like this, nickel atoms have become like this, agglomerated towards, right, one is sitting on the other, not a very good design of a catalyst. So, we compare the catalyst activity in terms of this turnover frequency, right. So, turnover frequency which is actually quantifies the specific activity of a catalyst center for a special reaction under defined reaction conditions, right. So, when I say this catalytic center, these are these nickel sites which are available on the surface, right. So, different, this is active centers, because on this the adsorption of a reactant molecule takes place. The molecule A comes and adsorb on these active centers, right, not on the support side, because it is a kind of specific reaction. So, that is what the meaning is special reaction here, right. This word has importance here, special reaction under defined reaction condition, very important term, because I told catalyst is very specific in their action. So, if I have a ethanol molecule, it can adsorb on nickel, but if I have some molecule like say carbon dioxide, it may not adsorb on nickel, right. So, that is what the when you say the specific action. So, a specific gas molecule will adsorb on specific substrate or metal, right. So, that is the key, and that deposition will take place only on the active sites. So, we call them active centers here. So, the word which is written here, the catalytic center, is also known as active center, which is nickel basically, but not nickel, the active nickel. There may be, you can have 100 gram nickel, the reaction may not take place, right, because you have not activated it properly, right. They have made a cluster, they have agglomerated. So, that is why the concept of nanoparticles or nanocrystal size is important, right. Smaller the size, it will have larger surface area per unit volume, right, more exposure to the surface, right, aluminum. So, what I am talking here, the turnover frequency is generally quantifying the activity of a catalyst under a given condition of temperature, reaction condition for a given reaction, right. So, by definition it is number of molecular reactions or catalytic cycles occurring at a center per unit time. So, how many gas molecules adsorb on nickel surface per unit time, right, per unit active center. So, now it is not the 10% nickel, it is not the 20% nickel, it is the active amount of nickel which is available on the surface, right. So, how we calculate, how we define this active surface available on the surface? We measure the dispersion. So, another definition is known as dispersion, which we will see later, but basically the dispersion is the fraction of the surface which is exposed for chemical reaction or available for chemical reaction, right, and that is just measured in terms of the fractional concentration, right. So, if I say that only dispersion is 10%, so it means out of these 10% nickel, only 10% are nickel sites are available for chemical reaction. So, rest is a waste, right. You have 10% dispersion, 90% is a waste, because it is agglomerated like this, one over other. So, this site is not available for chemical reaction now, which is on the lower side. So, this is the meaning of dispersion. So, we need a catalyst support or good catalyst support on which the dispersion is like this, right. So, that is again a very important concept or key for catalyst preparation, how to get good dispersion, and that is what I told, the concept of nano science or nano material, right. So, catalyst is related to your material science, right, and the concept is known as nano catalysis. So, we talk a term nano catalysis also, where we want high dispersion, right. The platinum, if you take nanoparticles of platinum, it can have the oxidation of CO even at room temperature, but the problem is that these nanoparticles are not very stable, they agglomerate faster. So, how to make them stable is again an issue, right. And so, this is what the R&D or research work, where we need to develop these kind of nanoparticles, nanocatalysts for the reaction, where the activity becomes very high, right. A low concentration of the metal will be effective. So, you are not consuming that much 10%, 20% or 50% of the metal, right. So, they are very precious. So, some of the values, tentative values, if you look at for heterogeneous catalyst reaction, the number of active center is derived usually from the adsorption method. So, this is what I was talking for measuring the dispersion in a catalyst. So, we will talk on this term later in different lecture. So, basically now by definition the turnover frequency is nothing but the number of molecules which are adsorbed on the surface, right, per unit active site per unit time, right. So, if you look at the value, so molecules divided by time, right. So, unit will have something like time inverse. So, if you look at for most of the heterogeneous reactions, the turnover frequency comes in the range of 10 to the minus 2 to 10 power 2, right. So, per second, and if you have something like enzymatic reaction, it has the value of 10 to the power 3 to 10 to the power 7 per second. So, very high value for the enzymatic reaction, that is why they are being considered, right. The turnover number of molecules which are adsorbing per unit time per unit site is very high, right. Turnover frequency is very high, turnover number is high, right. So, this talks in terms of the catalytic life cycle also. So, faster reaction can happen on this, right. Same thing here, the turnover frequency is generally the volumetric units which are defined, volumetric rate of reaction divided by number of centers divided by per unit volume of the total sites. Another definition is turnover number, which is just inverse of the turnover frequency, because they are interrelated. So, turnover number basically talks in terms of the lifetime of a catalyst, that how many time the catalyst can be used for the process, right. So, the turnover number specifies the maximum use that can be made of a catalyst for a special reaction, again under defined condition, by a number of molecular reaction or reaction cycles occurring at a reactive center up to the deactivation. So, means suppose the catalyst, as I said, that it can be reused again and again, right, but does not mean that throughout it can be reused, because activity of a catalyst, what we talk the stability, that decrease with time. Now, whether it is a good catalyst or bad catalyst, the activity may drop faster, activity may drop relatively slower, right. So, if the catalyst activity drops, then you have to look at the turnover number with time to time, right. So, then you are calculating that for how many time this catalyst can be used in a given reaction. So, generally you must have heard that after 3 years the catalyst has to be replaced, right. All these design company, whatever, for fertilizer industry or refinery, generally the catalyst life is very specific. So, for 3 year or 5 year or 6 months they are used, right. So, the idea is that you have to relate this in terms of the productivity, because once the catalyst deactivates, its activity drops. So, deactivation does not mean that activity is reduced to just 0, right. The activity is reduced to a level which is not economical to run the reactor, right. So, suppose the benchmark gives in terms of productivity, right, you are producing 10,000 tons per day, when the activity is dropped, so suppose 70%, so it means you are just producing 7,000, right. So, whether this is acceptable to the company, and depending upon that the catalyst has to be replaced or some fresh catalyst is to be added, right. So, this concept of turnover number is that for how many times the catalyst can be repeatedly reused under identical condition, right. So, this is what the very specific definition, that the number of molecular reactions or cycles occurring at a relative center up to a decay activity, right. So, decay activity can be a defined guideline. So, the relationship between turnover frequency and turnover number, that is turnover number is nothing but turnover frequency multiplied by the lifetime of the catalyst, right. So, turnover frequency has the unit of time inverse, lifetime of catalyst has the unit of time. So, this is the number of time, I can say 10,000 times the catalyst can be used, right, or 50,000 times the catalyst can be used. So, I can compare the two catalysts A and B based on this performance, right. So, for the industrial application, generally the desired is that the turnover frequency should be of the order of 10 to the power 6 to 10 to the power 7. So, these are representing the powers, right. So, 10 to the power 6 to 10 to the power 7, this should be the approximate reuse of the catalyst in the process, right. So, that is what I said, that if the catalyst is highly active, it may deactivate also faster. So, it may not be good, right. So, FCC catalyst has this kind of problems, right. So, they deactivate much faster. So, you need a different kind of reactors. So, fluidized bed reactors are used or moving bed reactors are used. So, the reactor design is related to the catalyst performance in terms of activity, in terms of selectivity, and definitely the other reaction optimization process conditions also, right. The definition of selectivity, as I defined earlier also, so there are numerous definitions which have been used, but most common definition, if you look at here, a reactant, this can give you P, which is the desired product, right, and it can give you P1 and P2, which is your undesired or side product, right. So, a kind of parallel reaction. Similarly, this is a sequential or series reaction where A goes to P and then P goes to P1. The desired is this one. So, the how do we define selectivity is just simply the moles of the desired product divided by the moles of the reactant reacted, right. This is very important specific definition. Generally, the what we are writing, the definition says that the moles of the desired product divided by stoichiometric coefficient of that product, right, and divided by moles of the reactant reacted divided by stoichiometric coefficient of the reactant. That is very general definition. So, the basic thing idea is that here, if I write that Na gives you Mb, right, and there are some other reactions also in parallel. So, selectivity is generally used for the where these are multiple kind of reactions. So, what I am defining that moles of the desired product. So, whatever the S of B divide by its stoichiometric coefficient divide by the moles of reactant reacted A reacted. So, that is nothing but whatever the delta what I am writing concentration difference of A, right, divide by its stoichiometric coefficient. So, this is generally a definition for selectivity, but there can be other definition. As I said, sometimes we define it moles of the product B formed divided by moles of the product C formed per mole. So, desired product divided by undesired product. So, there can be different definitions, because all of the time when we talk a reactor design, we relate the reactor concentrations or feed concentration in terms of reactants and products, and finally, when we optimize or compare a catalyst, we talk in terms of the selectivity. So, different researchers or for different reactions, the different definitions of the selectivity may be used, but when you look at your stoichiometry or mole balance equation, that will not change, right, because we are talking in terms of the reactants transform into the product. So, when you write a mole balance, it will remain same, right. So, here there is just a basis that per mole of this, if you look at the comparison for, because m moles of B are produced, so per mole of B produced, how many moles of this are produced. Similarly, this is what of the reaction. So, basically it is nothing but you are writing in terms of limiting component, A gives you m by n times B, something like this in terms of limiting reactant, right. So, all of you must have been learned this thing before. So, stability definition we have again talked. So, in that case, the chemical, thermal and mechanical stability of catalyst determines its lifetime, right, for an industrial reactor. So, when we look at the stability of a catalyst, then you are talking in terms of activity mainly. So, the definition is, generally we define a term known as activity A, right. So, activity A is defined in general the fresh catalyst rate or rate at any time t divided by rate when the catalyst was fresh, t is equal to 0, right. So, what is the definition is that the catalyst, if this is the activity of a catalyst, right, and when I say that the catalyst is good, so my activity A versus time activity should always be 1. It means catalyst is not deactivating for a long time. So, I will continue this part in the next lecture. I think time is up. So, I will continue it next time.